Good morning, everyone. We're going to continue in Chapter 5, hopefully finish Chapter 5 up here today. We were working on this problem at the very end of class, and I was, of course, going very quickly through it. I mentioned this type of problem tends not to really even appear on exam, so I don't want to dwell too much on this problem. It is actually pretty easy to set up, though, so that's the only reason why I want to come back to this problem, is that even though we tend not to test this problem for some reason on our common 1210 exams, it's a pretty straightforward problem, and it just involves a slightly different form of calorimetry from last time. And then if we get through all of our notes today, I'll have a review problem. If not, we'll look at it into the rest of the week on reviewing the first type of calorimetry we looked at last week. But constant volume calorimetry is really the same basic idea, that we have some type of reaction taking place where we have a heat change occurring from a reaction that's taking place. We see that the calorimeter's temperature is increasing from 20 degrees to 26.589. So the calorimeter temperature is going up. The calorimeter is the surroundings of the reaction. Remember, we can never really put a thermometer on the reaction. We can only touch the surroundings of the reaction. So the temperature of the surroundings is increasing. So the heat of the surroundings is going up, and that's because the reaction lost heat. So the reaction loses heat during this reaction. And so that's the definition of an exothermic reaction. So we had an exothermic reaction taking place inside this calorimeter. And in general, we're studying combustion reactions. And combustion reactions by nature are exothermic. That's why they take place with a flame. And so we have the heat capacity of the calorimeter is this value here. So the idea is that the water temperature is going to go up because the calorimeter where the reaction took place is going to get hot due to that reaction that was exothermic taking place in it. And so that's going to make the water temperature increase inside that calorimeter. And then you're assuming that this is like an insulated environment so that the temperature can go up inside the calorimeter and not be lost to its outer surroundings. So you have this thing take place inside of like a giant Stanley or something that's insulated is the idea. And so then we're tracking the heat change of the reaction by relating it to the surroundings heat change. And then the surroundings heat change is the heat change of the calorimeter, because it's like the entire calorimeter surrounds that reaction. And so the calorimeter is the surroundings of the reaction. And so you can relate the Q reaction to the negative C-cal times delta T, because our heat capacity, if you look at the units in the problem, is kJs per Kelvin. So 10.94 kJs per Kelvin. All we need to do is multiply that by our delta T. And so we take the 10.94 with the minus sign out front. The minus sign just comes from the reaction to the surroundings is always that opposite relationship. And then we get negative 10.94 times 6.589. So let's work that out real quick and finish the problem up and move on to our next topic. But 10.94 times 6.589 is negative 72.08. And then our units here, just kJs, because it's kJs per Kelvin times Kelvin. And also remember your delta T in degrees C, your 6.589 temperature increase is the same in Kelvin. That's 6.589 Kelvin, so we don't need to do any temperature conversions here. And then this is the heat that is released when that 1.5 gram sample reacts. If we had a smaller sample, presumably the temperature would have went up by a less quantity. If we had a bigger sample, we would have seen a bigger temperature increase. So this is the heat that's exchanged or related to that 1.500 gram sample that's combusting. So what you want to divide by here is whatever it was that was the limiting reactant and whatever the reaction was that took place. And it's really, usually in these problems, we usually try to be pretty clear so you don't have to solve a limiting versus excess reactant problem like we're told. You have heptane combusting in a calorimeter with excess O2. So we know the O2 is not limiting, so of course our limiting reactant is that heptane sample. And then we want the heat of combustion in kJs per mole of heptane. So all we need to do is multiply by the molar mass. So we take the molar mass given in the problem, 100.21 grams per mole. That's how we get the kJs per mole for the enthalpy of combustion of this compound. So we just go heat per quantity of reactant, convert to moles, and then we answer the first part of that question. So divide by 1.5 times 100.21 is negative 48.16 kJs per mole. And if we were to write the balanced combustion reaction, heptane is C7H16. I'm surprised I didn't give that. Oh, I did give it the problem. just wasn't looking. So we give the formula in the problem. We know that the combustion reaction is just this one here, forming CO2 and water. Need 7 CO2s to balance the 7 carbons. Let's do 8 waters to balance the 16 hydrogens on both sides. And so then that'll be 14 plus 8 is 22 O's. And so in form of O2, that'll be 11. So C7H16 plus 11 O2 goes to 7 CO2 plus 8 waters. Okay, and so the delta H of this balanced combustion reaction, we would look at the combustion per mole of C7H16 and just see that there's 1 mole in this balanced reaction. So the delta H of this reaction, oops, that's not a delta sign. The delta H of this reaction would be equal to minus 4816, just now kJs. So the per mole just goes to times the 1 mole of C7H16 in that balanced reaction. So our delta H is a reaction, usually just units of energy. We're assuming moles for each of the substances in our chemical reaction. Okay, so let's move off this topic, and like sort of the idea of calorimetry is where we get our delta H's from. So it's just in the lab, it's an experiment that we can do to determine delta H's of reaction. And then once we have a bunch of delta H's of reaction, we can use them to find other delta H's of reaction. That's going to lead us into our Hess's law topic. And we've seen an example already of Hess's law kind of worked out for us. But a problem here that we can use Hess's law to help us solve is where we have some reaction like this one here. Let's say we want to know the delta H of this reaction. Can we use the delta H's of other reactions to sum up to our desired reaction? So like let's say the NO plus O goes to NO2. Let's say that's a problem that we want to know the delta H of that we just can't directly study that in the lab. So let's say for whatever reason we can't put that into a calorimeter and study directly that reaction, but we can somehow study these reactions here. So let's say we have this known information from other experiments that have been done. Let's say I know NO plus O3. O3 is ozone, but NO plus ozone goes to NO2 plus O2. We know the delta H of that reaction is minus 189.9. We know ozone to O2. So O3 to 3 halves O2. We know the delta H of that reaction. Again, that would be 1 mole of ozone turning into 3.5 moles of O2 has a delta H minus 142.3. And the O2 bond breaking into 2 O atoms, we know that that's plus 495.0 kJs. So if we know those, can we rearrange those reactions such that they add up to this desired reaction? So if I just add the 3 reactions up as is, it doesn't quite work. If I had these 3 reactions up, it would be like NO plus 2O3 plus O2 go to a set of products that nothing's balancing out to our desired reaction. So what I need to do is I need to flip or manipulate the coefficients by some ratio relative to each other such that they add up to our desired reaction. So what I kind of start with here is just trying to look and see I have NO here, I have NO here. So this first reaction is actually good written as is. So I'm going to start just by rewriting the first reaction. And I know that this is in the right quantity and in the right direction. Because the question is, do I need to flip the reaction? Do I need to double the coefficients? Do I need to cut them in half? I'm going to leave this one as is because it gives me one of the reactants in the reactant side, gives me one of the products in the product side, and then those aren't in the other 2 reactions is the other key. Is I'm kind of looking for a reactant or product that's only in one of the reactions. So then if I look at the other reactant, O2, O2 is on the product side here, but I just have 1 O. And if I look at the other reactions, I don't see any O atoms, just plain O's. One other detail to quickly note, everything's a gas here. So everything's gaseous, so I'm just going to neglect writing gas a bunch of times. Sometimes we might have to pay careful attention. Sometimes we might see water gas versus water liquid and have to pay attention to phase because we have to match the right physical state up on each of the sides of the reaction. But this reaction here, I don't have to worry about that at least. So I'm going to neglect writing the gas symbol every time. Okay, so at least I've spotted the O is over here, and I need it on the reactant side. So if I write this reaction here, 2 O atoms forming O2. I know the delta H of that reaction should be flipped, so this should be minus 495.0 kJs. And then I need just 1O, so I need to cut these coefficients in half. So I need to put a half through the whole reaction, and so that'll make 1O goes to a half O2. So let me get rid of the sort of half on the parentheses here. So I'm gonna have 1O go to a half O2. So I've cut the coefficients of that reaction now in half. So I'm gonna cut the coefficient of that reaction in half. So I'm gonna take the minus 495, so 495.0, I'm going to multiply that by a half. So I flipped it from the original reaction, so negative, and then cut the coefficients in half, so a half times that delta H. And then the middle reaction, you may think you don't need it, but we actually need it to get rid of ozone because our overall reaction we're trying to add up to. So imagine we're just adding our reactions up. Right now, it would add up to NO plus O3 plus O goes to NO2 plus O2 plus a half O2. That doesn't quite balance out right. So what if I take this middle reaction here and use it to cancel out the ozone, but on the product side? So if I flip that reaction, the middle one, to have my O3 on the product side, and my 3 halves O2 on the product side, then the delta H of that reaction would be flipped. So this will be negative of negative 142.3. This will be plus 142.3 kJs. So if you flip the reaction, you just flip the sign. So it was positive becomes negative, it was negative becomes positive. And so this is just a puzzle. It's like, I want to find a way to add these reactions up so that they add up to my desired reaction, and then I need to figure out how their delta H's manipulate, how I need to change their delta H's, because I'm then just going to add up the delta H's. So if I can add the reactions up, I should be able just to sum up their delta H's, as long as I've gone through the task of correcting the delta H's for flipping and changing coefficients. Okay, so let's see if we add up right. So our O3 on both sides cancels. And then I have O2 plus a half O2, that's 3 halves O2, that then cancel with the 3 halves O2 here. And so what's left is NO plus O goes to NO2. So Hess's law is just a puzzle. It's like, how do we rearrange the reactions so that they sum up to the desired new reaction? And then how did we have to adjust the delta H's accordingly? And so now I should just be able to take the minus 189 and then plus negative 0.5 times 495 and then plus 142.3. So I add all these up, I get negative 294.2 kJs. So the delta H of our reaction should be negative 294.2 kilojoules. I'm going to double check. I got negative 295.1, so I don't know what I put in wrong the first time. Does anybody else do the math here? Got 295.1. So I must have put something wrong in, so it's good that I double checked, but it was. Okay, so Hess's law. It's useful because we can have ways of studying reactions that we can then manipulate to solve the delta H's of new reactions. So the point of this kind of part of the chapter is seeing how do we go from some experiments where we find delta H's to then putting those experiments together to find other new delta H's that maybe we can't directly study in the laboratory. Okay, so that's Hess's law. Now, the next kind of topic is, well, how can we more generalized come up with like a way to tabulate enthalpies of substances so we can then look up the delta H's of, say, all of our products and reactants in a reaction to solve the delta H as just being the sum of the products minus the sum of the reactants enthalpies. And the way we do this is we define something called the enthalpy of formation that we'll then tabulate and then put into tables or in appendices in your textbook. We put these into things like the C or C index so you can look these up. But these are values that you can then tabulate so you can use to just take the reactants and products for any reaction and just be able to plug them in and solve the delta H of a reaction. So the idea of a standard enthalpy of formation, though, is it's not like we tabulate the absolute or the total enthalpy of each molecule. We actually tabulate a change of enthalpy of a molecule or compound being formed from its elements in their most standard or most stable states at room temperature. So 1 mole of product is produced from its elements, but the elements are in whatever their most stable form is at room temperature. Now, the periodic table is somewhat complicated, so we're going to have to break it down into elements that we can make sense of. And then there's going to be a few, like if you get into things like phosphorus or like tellurium, things like that get complicated. So we're only going to focus on sort of the key elements here. Like O2, that is the most stable form of oxygen at room temperature, is the O2 molecule. So O2 gas would be formed from itself, and so therefore is defined to have a 0 delta HF. So when you think, I'm going to form on the product side, I'm going to write as the product 1 mole of a compound, or of a molecule here. So 1 mole of a substance, and I'm going to form the substance from whatever its elements are, and then I'm going to have to either figure out what the most stable form of those elements are, or maybe look up what their 0 delta HF states are. So O3, we mentioned earlier, that's ozone. That's what you call an allotrope, a different form of the same element. Some elements have these, most don't. Like sodium is just sodium metal in its most common form. There's no other form of sodium that's common at room temperature. But ozone does have this issue. We have O2 and O3. O3 exists in the ozone layer in the atmosphere. It's actually protective of UV rays. It's a very important molecule in the atmosphere. There was a time when we were using like a hairspray that was actually leading to CFCs. Refrigerants do this too, but a refrigerant released in the atmosphere that would indirectly destroy the ozone layer. So this is actually a problem we solved with science in the late 80s into the early 90s that actually changed a lot of refrigerants that we use. So it's actually a good example of science being used productively to solve a big problem. But O3, important molecule, different form of oxygen, important in the atmosphere. Carbon does this too. Carbon has allotropes. Carbon has diamond versus graphite. There's carbon nanotubes, there's buckyballs. Those are all different forms of carbon. The most two common forms that you find in nature are graphite and diamond for carbon, and it turns out graphite's the most stable, but we'll talk about that in a minute. But so O3 is going to form off of O2, and for this reaction, we're going to always form 1 mole on the product side, so we're going to have a reaction that's okay to have fractions in a proper balanced reaction. So I need a 3/2 in front of O2. In fact, this was the reaction from the previous page. But 3/2 O2 going to O3 would be the properly written what we call formation reaction of ozone. So a formation reaction form 1 mole of one substance on the product side, and then elements in their most stable states on the left reactant side. And so O2 gas will be oxygen, and the gaseous elements are the ones that are pretty easy, like H2, O2, N2, F2, Cl2, Br2, I2. Those are the most common forms of those elements. The only weird ones where you get into Br2 is a liquid, I2 is a solid. I don't know if we'd expect you to know that, but only like H2, N2, O2, F2, Cl2 are the diatomic gases at room temperature. But anyways, so our 3/2 O2, the delta H of that reaction, positive 142.3. Sometimes we can make sense of the sign, sometimes we can't, of the delta H. It might make sense that ozone is less stable than O2. That's one of the reasons why O2 might predominate at room temperature. But there is this issue of it's really the delta G that you need to know that would tell you if something's more stable or not. So it's really the substance that has the lower delta G. It turns out O2 has the lower delta G. You'll learn about that in chapter 19 later. So for CO2, if we're forming CO2, we need to form it off the most stable form of carbon at room temperature. And you just have to know that. And it turns out that the form of carbon is either, you're going to see this written as just simply carbon solid, is one way to write that. Sometimes we write a comma for graphite since carbon has other forms. So carbon graphite is the most stable form of carbon. If you just see carbon solid, that's what we mean by the most stable form of carbon in its solid form. And then plus O2 gas goes to CO2 gas, and so the delta H of that negative. Most molecules are negative. It doesn't have to be negative, but it's usually the case that molecules tend to have a negative delta HF. There are some stable molecules that have positive delta HFs, again, because it's really the delta G that matters. But usually molecules are more stable than their elements. That's why they exist as molecules more predominantly. So CO2, and you don't have to memorize these delta H's. It's just kind of showing you that the delta HF of CO2 would be the formation reaction of CO2 from its elements. And so we usually list delta HFs as either the value in kJs per mole is a property of the substance, or we think the delta H of the reaction, since there's 1 mole, just in units of kJ. Since we always write these reactions with 1 mole, the delta H corresponds to the same number in kJs per mole with the delta H of the reaction in kJs. There's a lot, and just basically saying if you write these per mole, there's always 1 mole. So the mole is always canceling itself out for the delta H of the reaction. So the delta H of the reaction forming 1 mole has the same numerical value for the delta H in kJs versus the value in kJs per mole. So water gas, it would be formed from H2 gas for hydrogen, and then O2 going to a fraction, a half O2. So H2 is the most stable form of hydrogen, graphite's the most stable form of carbon, O2 is the most stable form of oxygen, and so then we have that associated delta HF for water gas. Now, water liquid should have a different delta HF from water gas, but then the reaction is the same reaction, though. You may say, when I see water as a liquid, do I need to change H2 to a liquid, O2 to a liquid? No, those stay the same form. It's still the same form of hydrogen gas, and then a half O2 gas. So we don't change anything on the left side just because we changed the physical state on the product side. We just now have a new delta H. We just have a new enthalpy of formation. And then the utility here is you could look up, like let's say you wanted to know the reaction of water gas to water liquid as a delta H. Well, you just take the product minus the reactant. We'll just take this number minus that number. Just take the sum of the products minus the sum of the reactants. That's actually on the next slide. But if you want to know a reaction now using these delta HFs, you just apply the idea that you take the sum of the products minus the sum of the reactants. You take your delta. So there's products minus reactants. So we'd have minus 285.83 kJs per mole times a mole, which reduces down to just that number of kJs, and then minus 241.83 kJs per mole, again, times 1 mole. So the mole unit goes away. So we'd have minus 285.83, and then minus negative 241.83. Should a gas going to a liquid be exothermic or endothermic? We can usually predict phase changes. A gas to a liquid, that should give heat off. If you think of the opposite, if you think liquid going to gas, a liquid boiling should require the absorption of energy. So the liquid to gas, that makes more sense to me, that has to have a positive delta HF, and if I flip that, it has to have a negative. And I get the right sign out here. This is negative 44.0 kJs. So the idea of enthalpies of formation is we tabulate them as these formation reactions, but their utility is that we can then just plug and chug them into the sum of the products minus the sum of the reactants. Delta H is the calculator delta H of a new reaction. So it gives us a way to calculate delta H's of reaction if we can just look up all of the reactant and products delta HFs. One more here we see listed is CH4. So again, carbon solid, you'll see it written this way a lot, just as carbon solid, assuming it's graphite. Sometimes you'll see graphite written out, sometimes you won't. But if you saw diamond, that would be wrong. If you saw carbon nanotubes or something, that would not be the right form of carbon. And plus 2H2. So just balancing out the reaction to make our 1 mole of product. Now, if you're wondering, how does this work, or why does this work? Why do we tabulate the formations and not just the absolute enthalpies? Well, it turns out it's hard to study the absolute enthalpy of a substance. It's easier to study the change of enthalpies. It's easier to study changes of energy than absolute energies. That's one reason. And then number two is that if we tabulate these, they work just the same as if they were the absolute energies. And we'll see why through the next couple of slides. Okay, so which common elements and physical states should you know so that you can recognize that as the substance in its most stable state at room temperature and has a 0 delta HF? So I would expect that you can recognize the gases like we mentioned earlier, like H2, N2, O2, F2, Cl2, and then all of our noble gases. And so that would be the gaseous elements that I expect you to know on the periodic table and what their form is. So we have diatomics, except for the noble gases, being monoatomic gases. And so like the most stable form of like argon would be, of course, this argon gas. Neon gas, etc. There's only 2 liquids on the periodic table for our elements, Br2 and mercury. And so Br2 is bromine, and I think we pick up its Br2 just from the other halogens being diatomic, but it just turns out to be a liquid. I've probably never seen Br2 liquid where you have to know its delta HF is 0, but if you know it's the only other liquid on the periodic table other than mercury, you at least pick up pretty easily that Br2 liquid delta HF is 0. Hg liquid would be mercury. And then what about our solids? Well, our metals are pretty easy because it would just be the metal solid like sodium solid, iron solid, calcium solid. Very, very easy for our other metals other than mercury. That's the only liquid. We have carbon graphite. Again, sometimes you see it solid, graphite, sometimes just solid. We're assuming that's graphite. These, I don't think you'll see these many examples, but I2 is a solid, diatomic. And then there's a white phosphorus versus a red. I've never seen us ask about or have you memorized that phosphorus white versus sulfur rhombic. Those are more technical details that if you're taking like inorganic chemistry, you might see again later. But the primary ones to know are just the metals, carbon. I think bromine's worth knowing, and then these gases here. So I think these are the key ones just to know and recognize that those are your 0 delta HFs. And which elements are not, so then how can we recognize things that look like elements that might have a 0 delta HF that actually don't have a 0 delta HF? Like hydrogen atom. We get a hydrogen atom by breaking the bond in H2. That's going to take energy. We'll see that at the very end of the chapter. If we take something that's a bond like H2, if we want to break the bond, that molecule has to absorb energy to break that bond. So the H atom can't have a 0 delta HF. Same thing with O atom. We'd have to break the bond in O2. There has to be energy holding those 2 atoms together that has to be overcome. So O2 would probably have a positive delta HF, not be 0. Some other form of carbon wouldn't be 0. Some other form of phosphorus, if we told you phosphorus white, like on a test, I could see saying phosphorus white is the most stable form of phosphorus. Would phosphorus red be expected to have a 0 delta HF? Probably not, because then it would have been the most stable form. Sodium gas. So if you change the physical state, you're going to change the enthalpy. So you have to have sodium solid, calcium solid. If you put an AQ, a tag, those don't have 0 delta HFs by definition. It's only iron solid, only N2 gas. So if you change the physical state from the most stable form, then that won't have a 0 delta HF. You can sort of think there's going to be an enthalpy associated with N2 gas to N2 liquid. There's going to be an enthalpy associated with sodium solid to sodium gas. You may or may not be able to predict the sign. You usually can predict the sign, but it's not going to be 0 for those other forms with other physical states. Okay, so I just want us to be able to write and understand the formation reaction so we can understand what forms we write the reactants in to balance out those reactions. And then the utility of those reactions is to find the delta H's. So the whole point of our delta H's of formation is to solve for delta H's of reaction. And so let's look at this combustion reaction. We've seen this a few times. The CH4 plus O2 goes to CO2 plus water. We have it balanced up. So what we can do here is we can look up, like back in our notes, for example, because they're all in our notes here, but we could look up delta HF values for the reactants and products here, and then accordingly solve for the reactions delta H. And so these were all in the previous slide. I should have just thrown them on here because I'm going to have to flip back. But I remember CO2's, like, so what I would do here is go to my index, go to my CRC, go to the back of my textbook, go to a table. We'll give you this information usually within a problem on the test, so you don't actually have to look these up on a test or anything. But 395.5, okay, so I've tabulated these values from the previous page. So 74.8 for CH4 minus 393.5 kJs per mole for CO2. and then making sure we grab the water gas, not the water liquid, but it's minus 241.82 for water as a gas. Now, what I should be able to do to calculate my delta H of reaction is take the sum of the product's delta HFs and then subtract the reactants, which makes a lot of sense. Products minus reactants for our delta. And then we just have to account for our stoichiometry. So I'll have 1 mole for CO2 times the negative 393.5 kJs per mole. Then I'm summing up the reactants. So I'm going to add, for water now, 2 moles times the negative 241.82 kJs per mole. And so that's the sum of the products. And now we need to subtract the sum of the reactants. So that'll just be 1 mole for the CH4 times negative 74.8 kJs per mole. Now I could write this plus 2 moles, but it's just times 0. So usually we'll not even write that, but the O2 is the most stable form of oxygen, of course, has a 0 delta HF. The way we tend to do this on a test is we'll give you a reaction like this or some other reaction that has, 3 or 4 molecules in it. Usually one of them is one of the substances we have to recognize that has a 0 delta HF. And so usually we'll give you all but the 0 delta HF substance, the one that's 0, we expect that you recognize as 0. We'll give you the other 3, and then you can calculate the delta H of the reaction. And then we love to put this on a multiple choice test. We love to have an option of not enough info, because sometimes you think, well, I need the delta HF of O2. We expect that you know that that is 0. So we expect that you recognize the common elements in their stable states that have that 0 delta HF, so you can know that this we just have to know. And then the last thing is, well, there's a lot of things. I always say the last thing. Like a thing that's important is being careful with the minus signs. So when I put this in the calculator, I try to be very meticulous and do like negative 393.5. And I just always go plus 2 times, and then the negative 241.82. Like I try not to do the arithmetic. I try not to get so like cute with my math when I put it in the calculator that I'm doing like, I'm usually not like flipping that to a minus sign because I make mistakes with that. So I like to just be very careful doing negative 393.5 plus 2 times negative 241.82, and then the minus the 1 times negative 74.8. Again, I just try to put the minus in whenever I see a minus sign. Whenever something has a negative value, I put it in my calculator as a negative value. Sometimes we don't use a negative button on the calculator. I think it's very easy to use. I make less math mistakes, I feel like, when I just use that minus button. But anyways, this works out to be minus 802. Put it on my screen. Minus 802.3. And now my units just go to kJ. So we see all the moles are canceling. So you can see again why the delta H's of reaction aren't kJs per mole is because our moles have all canceled out because we've accounted for the moles of each substance in that reaction. So we now have like 3 ways to find delta H's of reaction. We can study a reaction in a calorimeter. We could have maybe studied this in a calorimeter, this particular reaction here. We could have used Hess's law, or then we can use the enthalpies of formation. If we know all the enthalpies of formation, can look them up, can have them handy and available, we can sum up the products minus the reactants very easily. Okay, so the idea of this chapter is just trying to see the heat changes the Q. Q is heat. The heat changes that accompany a reaction, we can get that from delta H, the enthalpy change of the reaction. So our enthalpies are delta H's. Sometimes we call these heats of reaction. The delta H is the heat or the enthalpy change of the reaction. You see here, this is exothermic like we expect. So you can even come back to the idea this is a combustion reaction, should be negative. It is negative. You can catch mistakes sometimes by thinking of the nature of our reactions. Okay, now, this is actually an interesting question, or like if you're thinking, well, why does this work? Like, why is it that I can just take these reactions, the delta HFs correspond to reactions. How is it that they work to furnish our given delta H's of reaction? So the way this kind of works is if you think of your product, CO2 and water, in terms of their formation reactions, we're forming those substances on the product side from their elements on the reactant side. And so in the case of CO2, it's carbon plus O2. In the case of H2O, in the case of water, it's H2 plus O2. And then I double the coefficients for water since there's two H2O in my balanced reaction. So if I'm thinking Hess's law, I'm just taking like the summation here of the CO2 and the water reactions, just doubling the water reaction because there's two of them. And then those are on the product side, so I just use those reactions as they were. So I'm using my delta HF reactions, just accounting for the number of moles within each to get my delta H of reaction. And then if you look at the CH4, from the formation reaction, I had to flip it. I had to flip that reaction to get CH4 onto the reactant side. And so I'm flipping my CH4 reaction, so CH4 is now starting on the reactant side and getting my elements for that on the product side. And so if you notice, all the elements here, well, except two of them, are canceling out. So my H2s are canceling, my graphites are canceling, my two O's aren't canceling because they're in the overall balance reaction. So that's how I get, by Hess's law, I'm just adding these reactions up. So CH4 plus the 2O2 goes to the CO2 plus water. So it's Hess's law in action on why these reactions as formation reactions work. So the idea is, if formation reactions come from their elements, and you have the formation of your products and the reactants, they're being formed from the same set of reactants relative to each other. So you can take the changes of the heats of formation to give you your delta H of reaction. Maybe you didn't need this slide, but if you're wondering why do those formation reactions work, why is it that we were tabulating formation reactions as chemical reactions, but then using them as like singular points? It's just because of the way Hess's law works. It's just the Hess's law works when I take the sum of the products, delta HFs, minus the sum of the reactants, delta HFs, just accounting for the number of moles on our product and reactant side. Now, let's say we're given a reaction. This actually goes back to that starting problem from today, the heptane combustion reaction. And so, which, like, let's even say we recall from that previous example that the delta H of combustion, the enthalpy of combustion of heptane was that minus 4816 kJs per mole. Since there's 1 mole here, that tells us again that the delta H of this reaction would be minus 4816 kJs. So just times the 1 mole of the C7H16. Now, given the CO2 and water values here for their delta HFs, can we solve for the heat of formation? Like, one of the things that calorimetry experiments gets you is if you know the delta HF of CO2, you know the delta HF of water, you do one of those experiments to determine the enthalpy of formation of a compound, the enthalpy of combustion of the compound. So we got the delta H of combustion of heptane. From that value is what you can calculate and determine the delta HF. So from the results here, we can solve and determine the delta HF, the enthalpy of formation, as an unknown. So this problem here is basically saying, if you know the delta H of the reaction, and you know all but one of the delta HFs, can you solve for the delta HF? Of course we can. So what we're going to do here is set up our delta H of reaction as being equal to the products minus the reactants. So I'm going to have 7 times the delta HF of CO2. Let me even be careful. Let me write 7 moles. So 7 moles times the delta HF of CO2 minus 393.51 kJs per mole. Adding the sum of the reactants, so plus 8 moles times negative 285.83. Notice that water is a liquid here and not a gas. There's a slight reason why it's a liquid here. The combustion takes place in a container, and the container doesn't allow water vapor to escape. So water condenses because it's a liquid at temperatures that are surrounding that cylinder. So not a big detail, but if you're wondering why water is a liquid, water can be a liquid in a combustion reaction if you can trap the water before it can float away. So the water didn't have a chance to float away, so it ends up condensing. Not a big detail, because we're just using the sign that's given in the problem and the delta H accordingly. And then, so that's the sum of the products, and then minus 1 mole times the delta HF of C7H16. And then like that's it for our reactant side. And then it's 11 times O2, but that's 0. Because the delta HF of O2, of course, is 0. And so all of this is equal to minus 4816 kJs. So all we need to do is a little bit of algebra. So let's work this part out here and then apply some algebra steps. So 7 times negative 393.51 plus 8 times negative 285.83. So that all works out to be negative 5,041.21 kJs, and then minus 1 mole times the delta HF of C7H16 is equal to that overall delta H of minus 4816. So that's the sum of the products minus the sum of the reactants equals the delta H of that reaction. So now this just becomes an algebra step. So I need to add 5,041.21 to both sides. So I take negative 4816 plus 5041.21. So I get negative 1 mole times the delta HF of C7H16 is equal to plus 225.21 kJs. So I've just added the 54, I added 5,041.21 to both sides. And then I'm just going to divide both sides by negative 1 mole. Just so I can solve for this. So my delta HF of C7H16 comes out to be negative 225.21. And then rounding it, we did an addition step and we only had the nearest ones placeholder, so that's why it'll get a 225 kJs per mole. But then I get kJs per mole to work out too. So it gives me my units out in the proper unit. For delta HFs in units of energy per mole. And so I just want you to see, this is experimentally how we determine delta HF values. We determine delta HF values by doing experiments like that bomb calorimetry experiment. I think our quiz is next. I still see a little bit of handwriting. I'll leave this up for another second or two. But if you usually navigate by Carmen, you can go to the quiz. I need to switch slides. I don't know what the keyword is, but I've been posting the PDF versions of slides if you haven't noticed. So I've been posting I know my handwriting's terrible, but I've been posting the PDF versions of my slides after class with whatever I handwrite. So if you've ever missed something or weren't sure what I wrote, if you wanted to zoom in or see it later outside of the video, you can see those PDFs. And I've posted them for all the lectures going backwards as well. Redox is our word for today. So our last topic are bond enthalpies. And I think this is a good topic to kind of, wrap the chapter up with, because why do reactions have, positive or negative signs of reaction has a lot to do with the nature of the bonds that are being made or broken during the course of a reaction. Now, bond enthalpies will help us try to understand some details. Like, for example, we were mentioning earlier, and if you have H2, it's going to take energy to break the bond. Anytime you have a bond, it takes energy to break. If you notice, all of our bond enthalpies are positive. There's no negative bond enthalpies. So bond energy is positive because it takes energy to break bonds. So like a molecule has to absorb energy to break its bonds. But then when we have new bonds being made, the question becomes, were the new bonds collectively stronger than the bonds we had to break to make those new bonds? It gives us a kind of interesting way to look at reactions as being a collection of broken bonds and the reactants and formed bonds in the products, and which one took more energy to break. Do we have to take more energy to break the bonds in the reactants? Do we get back more energy? And that would be an exothermic reaction, or do we get back weaker bonds, and then that would be what an endothermic reaction is. So this will give us a good mental picture of just forming stronger bonds as being exothermic, like a property of an exothermic reaction, and then forming weaker bonds being a property of an endothermic reaction. So the greater the bond enthalpy, then the stronger the bond. So a bond that takes more energy to break is net stronger. So our double and triple bonds, we'll come back to this a little bit more in chapters 8 and 9. Because right now, if I give you a formula, you couldn't necessarily tell unless you knew from prior chemistry if the molecule should have a double bond, single bond, triple bond, or whatever. So we need to learn a little bit about Lewis structures and bonding theory to be able to predict from formula what type of bonds things have. But if I show you like a carbon-carbon triple bond, that's going to be stronger than a carbon-carbon double bond. Now, at the same time, though, it's interesting that if you just had the complicated thing is you change the CH bond. So like a molecule that has a triple bond with carbon would only have 2 single bonds. So if you had like carbon triple to hydrogen, you maybe need to think about how that compares versus the energy of having like more CH bonds. Like C2H6 has 6 CH bonds and the 1 carbon-carbon triple. So there's a lot that goes on in molecules in terms of their stability, more than just the calculation of one single bond's energy. But bond energies go single versus double versus triple, increase in energy. So the greater the bond enthalpy, the stronger the bond. And then energy is always released if you then form a bond. So if I take fragments of atoms and make a bond out of those fragments, then that's going to release energy. So if I took 2 H's and form an H2, then that should be negative because it's just the simple flipping of the reaction. So our H2 value is like here. So the energy to break a hydrogen bond, 436 kJs per mole. But if I form an H2 from 2 H fragments, negative 436. So if we're forming bonds, then those are exothermic. And then we can use these bond enthalpies, but now this is just to approximate. This is the only topic in this chapter that leads us to an approximation and not a direct and exact calculation. Everything to this point in this chapter would be within experimental error, calculating our delta H's, correctly, what we would expect for our reactions and not be a prediction. This here turns out to be a prediction. And the explanation why is that our bond enthalpies are kind of like average bond enthalpies. Like a CH bond, 413 kJs per mole, there's all kinds of CH bonds where it might be, one might be 418, one might be 403, one might be 413 exactly. There's a range of values for a CH bond strength comparing if you're looking at CH4, C2H6, C3H8, the CH bond in acetylene, for example, has a slightly different CH bond strength than the average of 413. Sometimes also the first CH bond has a different strength than the second CH bond in a molecule. So we average out bond enthalpies so that you really don't get a perfect calculation, but you do get a prediction of enthalpies of reaction. So the first thing is you get an approximation of bond enthalpies, but then it ends up being the opposite. It ends up being the opposite of what you might think. We have to take the sum of the bonds we have to break in the reactants, and then the sum of the formed bonds in the products. And we'll have to see why that is. But this is a weird delta. We're going to calculate our delta by taking the sum of the values starting in the reactants and then subtracting the products. So most deltas are final minus initial. Most deltas are products minus reactants, but this one here ends up being reactants minus products. So we need to understand why this reaction here is kind of the backwards from what we have expected from most of our deltas. But it's just from the nature of the way bond enthalpies are a property of the reactant going forward. So let's try to see why it's reactants minus products. So if we're trying to approximate the delta H of this combustion reaction of methane, here the idea is we have to picture breaking all these bonds here. Is kind of saying if I have to break all those bonds, it's going to be that 413 kJs per mole from the previous slide times 4. We'll see some numbers thrown in. They're just on the next slide. So if you look ahead, you'll see some of the numbers thrown in. The O2 number is 495 kJs per mole is the bond strength of O2. I got to break 2 of those. So I got to do like 495 times 2. So the first thing I might do is just recognize, well, I got to like sort of fragment the CH4 and the O2 into their atom fragments and quantify how much energy will it take to break those bonds. That, of course, should be that should be endothermic. Should require the absorption of a lot of energy because I'm breaking all of those bonds that were stable. That's why those molecules existed. So I'm breaking what was holding those molecules together. So that requires the absorption of 2642 kJs per mole. Another thought here is that this isn't how combustion reactions take place. Like, this is an idea in this problem that we're using to approximate delta H's. When we do a combustion reaction, we don't like spontaneously break all the bonds and then instantly reform all the new bonds. Combustion reactions are very complicated. There's a very complicated series of steps that the molecules undergo. They undergo them very quickly. That's why combustion reactions go, kaboom. So they do those steps very quickly, but there's a lot of steps. It's very complicated. But if we're simplifying the mathematics of what the delta H can be approximated as, we take the sum of the energy it takes to break all those bonds. So just 413 times 4, 495 for O2 times the 2 O2s. Then we look and say, well, what are we making with those atom fragments? We're turning those atom fragments now into the CO2 molecule. So I'm making 2 of those double bonded COs. The CO bond strength is 799 kJs per mole. I'm making 2 of those bonds. So 799 times 2 are the bonds that we're making for the O2 or for the COs and CO2. Then I'm making 4 bonds between H and O. The HO bond's pretty strong, 463 kJs per mole, and I'm making 4 of those bonds. And then these have been flipped, so I'm taking the fragments and forming, so all of the bond enthalpies are now flipped. So this is now exothermic because I'm making bonds. And so making bonds is always exothermic. Now, but the question is, did it take more energy to break the bonds, or did I get more energy back when I made the new bonds? Of course, you can see here, I get back 3450 kJs when I make my new bonds. So I've made a collection of bonds that are now much stronger. Like, that's the whole point here, is seeing that our negative exothermic combustion reaction, we knew it was exothermic because we can see with our eyes. We know energy is being given off, and it's being given off because we're forming stronger bonds on average. So the way this works out is our 2642 minus 3450 give us a pretty good estimate. If you remember, it's minus 802. We get minus 808 here by using our bond enthalpies as a prediction of our delta H of reaction. So again, this is the only topic in this chapter. This is the only section where we're approximating anything. Everything else is a direct calculation. Nothing else in this chapter was an approximate enthalpy. This is an approximate enthalpy, but it's a pretty good approximation, but it lets us see the idea is that we're breaking weaker bonds and we're forming stronger bonds. That's a property of an exothermic reaction. The opposite of that, breaking stronger bonds and making weaker bonds, would be a property of an endothermic reaction. So if we flip this chemical reaction, we know the flip reaction should be plus 808, and the flip reaction would be that exact example, breaking weaker bonds, breaking stronger bonds to form weaker bonds. So hopefully this gives you a picture of what it means to be exothermic. This question here is just kind of like going back to the H2O2 combustion reaction we saw on the first day of class to take us kind of full circle back to day 1 when we saw, or I think that was on the second one. Was that whatever, I think it was the first day of lecture. We saw with our eyes energy being given off when that balloon goes kaboom, we see the flame take place, and it's because the products bonds are, now stable is another word, like what does stable mean? Stable is, more stable is stronger. Less, like weak bonds, that's not stable. Like weak bonds are unstable. And so we're starting with weaker bonds forming stronger bonds. So we're forming something more stable during that combustion reaction. So energy is given off because the products bonds are more stable than the reactants bonds. So more stable means stronger. All right, that's a good stopping point for today. We'll look at some review of calorimetry, but we'll be getting our start of chapter 6 on Wednesday. All right, guys, have a great day.